Walk into a wine shop and you'll see shelves packed with thousands of different labels. Globally, there are over 10,000 distinct grape varieties cultivated today, creating a massive agricultural industry. But genetically, almost every single bottle on those shelves, exactly 99.9% of the world's commercial wine, derives from just one species of plant, Vitis vinifera. For centuries, tracing the origin of this monolithic crop meant relying on Greek and Roman texts, or defaulting to the mythology of gods handing the vine down to mortals. Today, researchers bypass the written record entirely. Instead, they extract ancient DNA and chemical residues trapped inside millennia-old dirt and broken pottery. This molecular forensics work has pushed the timeline of human agriculture by thousands of years, revealing that every glass poured today traces back to a singular genetic accident. Look at these vessels from Gata Krili Gora, a Neolithic site in the South Caucasus. Dating back to roughly 6000 BC, they are among the earliest known examples of winemaking pottery. To test what these massive 300-liter clay jars once held, modern archaeologists use a technique called liquid chromatography mass spectrometry, or LC-MSS. This is a highly sensitive method that separates and identifies specific molecules within a complex mixture. Lodged deep inside the microscopic pores of the clay, they found tartaric acid. In the Near East, this specific organic acid is the primary biomarker for grapes. This raises a biological question. Out of all the available crops in the region, why did early humans choose to invest so heavily in farming this specific wild vine? This biological diagram illustrates the difference. Most wild Eurasian vines are dioecious, meaning they have separate male and female plants that rely on wind and insects to cross-pollinate. Vitis vinifera, however, carries a mutation making it a hermaphrodite. It has both male and female organs in a single flower, allowing it to reliably pollinate itself. Because it could self-pollinate, early farmers didn't have to plant unpredictable seeds. They could clone the vine through vegetative propagation, simply taking a cutting from a strong plant and rooting it in the soil, ensuring the resulting fruit would be consistently sweet. By exploiting a single genetic anomaly in a wild fruit, early humans gained the strict biological control required to turn a localized vine into a mass-produced agricultural staple. As cloned vines spread westward across the Mediterranean, ancient Greece built the infrastructure to scale this crop into a commercial engine. Greek agronomists introduced strict yield management and vine training, producing enough volume to fuel a massive maritime export network that shipped an estimated 10 million liters of wine into Gaul every single year. But mass transport introduced a logistical hurdle. The Greeks moved their product in clay amphoras, a highly porous material that allowed oxygen to seep in and quickly ruin the liquid inside. To seal the vessels, they applied a specific chemical additive directly to the containers and the wine itself, pine resin. During fermentation, the sap extracts herby aromatic compounds, notes of sage, rosemary, and ginger, directly into the liquid. It serves as a tool for intentional flavor manipulation, functioning separately from a preservative. That precise ancient chemical manipulation survives directly on today's market as the traditional Greek wine style known as retsina. The Greeks took the foundational biology of the vine and layered on their own chemical flavor manipulation, engineering the first global beverage industry. As those physical trade routes pushed further into Western Europe, the imported Mediterranean vines came into contact with wild, native European grape populations. This genetic network tree maps the paleogenomic data. It shows how the imported Vitis vinifera interbred heavily with those local wild vines, establishing the DNA foundation for the famous varietals we drink today. Because humans constantly crossed their best-performing plants, this family tree is incredibly tight. For example, crossing Sauvignon Blanc with Cabernet Franc resulted in a direct offspring, Cabernet Sauvignon. The global market appears to offer thousands of unique European wines, but their DNA reveals a remarkably narrow, tightly knit genetic monoculture. Out here in the modern global vineyard, that monoculture represents a critical vulnerability. Today, just 11 cultivars account for more than a third of all the wine produced worldwide. Because these millions of vines are practically identical on a genetic level, they share the exact same weaknesses. An entire global crop is highly susceptible to temperature shifts and the compounding effects of global warming. To protect the industry, researchers are now heading back to the original geographic cradle in the Near East and arid desert regions. They are hunting for ancient, heat-resistant DNA lineages that were left behind millennia ago. A glass of wine is a living, 8,000-year-old chemical artifact. To ensure it survives the climate challenges of the next century, we have to harness the exact genetic adaptations that allowed it to survive the last 80.